Okay, and there was a request to do Ralph's difficult question, question 15, in a not hand-waving way. In other words, to do it thoroughly and properly. So I aim to do this then. Alright, so let's look at the situation here. We have two equal masses there and a third mass here. They're all the same. And so what we expect will happen here is that these masses will both accelerate down, could be up, but we'll say they're down, together at the same speed. Because of symmetry, the situation they face is identical. And this one will accelerate in the opposite direction. Alright? They're connected by a string that presumably is massless and doesn't stretch. So whatever rate these accelerate, this one will accelerate with the same rate in the opposite direction. Now, there is tension in the string, and that tension provides a force. Here, it provides a force up, and here, the same force up, and here, the same force up, and here, the same force up. So all the tensions acting are vertical. And the tension is the same throughout. These are light frictionless pulleys, so whatever force is felt anywhere in the string is the same. Note that the previous question about tension was done rather poorly. So to note, if the tension in the string is T, then any object attached to the string feels a force of T. There, 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 and there. There's a force of T. So, and as I said before, the acceleration of this mass up and this mass up must match the acceleration of this mass down, or vice versa. I mean, yeah. So we can say that if we call this one 1, this one 2, and this one 3, we can say acceleration of block 1 is equal to the force on block 1, which is going to be T minus mg, divided by the mass of block 1. Alright? And this is exactly the same as the acceleration of block 3. Alright? Now, the acceleration of block 2, which is also the same, because except it might be in the opposite direction, is going to be 2t minus mg, because there's t there and t there pulling up, over m. And as I say, this must be equal to a1 and a3 in size, if not in direction. Okay. In fact, you can say that the direction will be opposite. Okay. So in actual fact, we can say it's going to be equal to the opposite of it, because if these are going down, clearly that's going up. So it's the opposite. So therefore we can write 2t minus mg over m is equal to the opposite of that, which we'll write as mg minus t over m. We can get rid of the m's on the bottom, and we can put the t over there, and we can get 3t is equal to an mg minus 3t equals 2mg. Okay, so 3t is 2mg. So t, the tension, is 2/3 mg. So now we need to find, we know the tension, we need to find the acceleration. We can find the acceleration of any of these blocks. So let's do 1, say. If we look at 1, we go, the acceleration is going to be the force, T minus mg over m, which is going to be 2/3 mg minus mg over m, which is going to be minus 1/3 g. Okay, which I've chosen up to be positive, so -1. So this accelerates downwards at a rate 1/3 g. That's not the one we were asked. We were asked about this one. So let's do that one specifically. Okay, so for 2, we can say that the acceleration is equal to the net force, which is 2t minus mg over m, which is equal to 2t is 4/3 g mg minus mg over m. 4/3 minus 1 is 1/3. 1/3 mg over m equals 1/3 g. So, and this is positive, and that's our positive direction, so it's upwards. Another way of looking at this problem that makes it seem a bit simpler is quite an easy way, which is to say that is equivalent to this. One pulley, on this side a mass m, and on this side a mass 2m. It's the same as that. You see, you've got two masses pulling down and one going up. So this is the same situation, and that's easier, well, that's pretty simple to solve. I'll leave it as an exercise for you to show that you get the same solution.